Michael, as you think about young people today and think about Michael Staab as a middle school student or high school student.
So I have to go back a few years to do that.
Yeah, I know, but those are some pretty formative years. So in that respect, tell us what habits you think you developed at that tender young age that have stood you in good stead on your career pathway. And then what habits do you think any student could start to implement daily that would make a difference in their future?
Well, for me personally, I always knew what I wanted to do. I wanted to work on spacecraft. And I knew what I had to do to get there. I knew that I was in for many years of mathematics and physics and long nights with very difficult classes, high school and college. And I knew what I was getting myself into, but I pretty much knew at that point that I wanted to build Mars rovers and lunar landers, and I was, wanting to, maybe put my hat in for flying as an astronaut someday. I potentially could still do that, but I kind of knew what I wanted to do, and that was, I think it's important to have what I call like 5-year goals and 25-year goals. The astronaut thing was always a 25-year goal. It was always so far in the future that I was, it's you can't sort of get too overwhelmed with, oh, what are all the things I have to do to get there? But it was a great sort of end goal years down the line that I could always push myself towards. What is the next thing that I have to do to keep going? And those set up little small goals. For this year, I'm gonna take these classes. I'm gonna work on these projects. I'm gonna get this internship. And you just over time, you just start building up, and then you look back at your resume. And I tell all the time, I'm like, wow, I can't believe all those things that I've already done. And if I didn't have that 20-year goal down the line that was, oh, I want to work on Mars rovers, I want to fly as an astronaut, then I wouldn't have all these experiences where I got to work at the Jet Propulsion Laboratory, I got to fly spacecraft around Saturn, I got to operate a Mars rover, now building a lunar space station. I mean, all those little things, they just add up. It's like having that 20-year goal down the line of, I want to work in space, I want to be an astronaut. That sort of was just my motivating factor. Just kept me straight on the course of, okay, these are the things I have to do, and these are the steps that I have to perform in order to get there. And I still kind of keep to that plan because I haven't been selected as an astronaut yet. I'm at the point where I'm totally okay if that never happens, because having that goal pretty much got me to the place that I am. I'm very happy with the things that I'm doing.
Do you feel like it's that goal alone that keeps you motivated, or what else can motivate people? Again, think middle school and high school. What can motivate kids that are really sometimes at a pretty awkward time in their lives to keep going?
Yeah. Going. Well, if it's not a 20-year goal, it could be something as easy as I want to graduate high school. I want to go to this college. We've all been through a very traumatic 18 plus months right now, and it's hard to stay motivated sometimes when you look at the state of the world, and we're slowly maybe coming back to a sense of normalcy. It's hard to stay motivated when it's like, oh, that thing is so far down the road. Why am I worried about it? So just setting up little goals. As an adult now, it's like, oh, I want to buy that house. Well, that house is maybe 5 years down the road if I save. If maybe I want to do that really neat part of engineering that I don't really have the experience for. So I'm going to say for the next 3 years, I'm going to take on maybe an extra task. It gives me that experience so I can get to that thing. I like having long-term goals just because they keep me motivated to keep pushing towards that big thing at the end of the road, the pod at the end of the rainbow. There's little gold coins along the way that you get as like little little rewards along the way. Oh, I got I got that internship that I really wanted. or I got to work on that project that I really wanted to do, or got to drive Mars rover. Never thought I'd get to do that, but just little goals is like, oh hey, this little nugget over here that they haven't opened. It's like, yeah, I think I'd like to go do that. May have not been in the cards on the path to that end goal, but it is something that's like that could still be really useful, and it's also really cool.
Awesome. Well, I heard a story about you.
I hope a good one.
It was, I feel like I may have told you about it. The attorney that I met in Wichita, whose son was a year or two behind you in school and attended camp and I think with McDonnell Douglas maybe in Kansas City.
Mm-hmm.
And he really credits you with keeping his son focused. And did this ringing any bells to you at all?
No, it's not ringing any bells.
Well, you absolutely made such an impression on this dad that he said, Michael Staab would just tell him to keep his head in the game and do his homework and stick with it every day in high school. So how do you think that young people, sometimes obviously unintentionally or intentionally, can look beyond themselves and support each other, not necessarily just as a team, because maybe you're not on the same team. This was an underclassman who you were just bringing along and being kind to. So why is that important, and how did you do it?
Again, I think as a high schooler, I knew what I wanted, and I remember the first day I walked into my high school physics class, and we were just doing introductions with the instructor, Mr. Burkamp over in Mays High School, and I told him literally the first day I'm going to wear an NASA. No straight face, no like balking at all. I'm going to work for NASA. That's what I want to do. I think that just helps with high school is kind of the time where you don't really know what you want to do. A lot of people don't know what they want to do. Even in college, they get I've been in school for 2 years and they've changed their degree 3 times because they don't know what they're doing, or they don't know what they want to do. I know what I want to do. I was going to work for NASA. I went to Wichita State. I majored in aerospace engineering because I wanted to be a rocket scientist. I knew that's what I wanted to do. I think having that very set plan of I know what I'm going to do, it kept me grounded. It kept me focused. And I think a lot of people kind of, it may sometimes unintentionally may see that as this kid knows what he wants. I knew what I want. He knows what he has to do, and I kept grounded and just kept grinding. Knew what I wanted to get. Eventually, I stopped grinding so hard because at some point you want to have some fun in life. But it's for I think I attracted maybe some sort of that that sort of motivation or that mindset of I knew where I wanted to go. I knew what I wanted to do, and I think a lot of people back in my high school, I think if I were someday to be selected as an astronaut, I don't think they would ever be surprised by it, because that was just who I was. It's just what I wanted to do. I knew what I wanted, and I just keep grinding towards it.
Awesome. So tell me about curiosity, and if that factored into what you were thinking about as you were heading toward your goal. How does that help you with your engineer mindset and problem solving? And how do you think it helps young people to stay curious?
So are we talking about Curiosity, the one that landed in 2012, or the one that landed in the one that I wrote?
I'm talking about Curiosity, the personality trait.
Oh, see, this is the thing. We hear names that are like, oh, are we talking about the rover? I know, it's so hard.
That's hilarious. No, just again, I'm going all woo-woo on you today. That's why I get the soft, fluffy questions, because I like to think about the underlying traits. And we're also trying to identify some of the ways that those traits manifest in the lives of people who've gone on to do some of the things that students want to do, even if, as you said, it is just getting out of high school. What helps you get through that or to that in the terms of meeting a goal, and is a curious and open and wondering kind of mindset one of those things?
Well, I mean, especially speaking for engineers, scientists discover what is, engineers create what is not. We take the foundations of physics and how nature works, and we create things that have never been done before, especially not natural devices, whether it's a rocket or literally under cars. Those are not naturally forming things. Engineering particularly, you have to have that trait of, you want to try and understand how something works, and sometimes it means digging down as deep into the details as you can get, to really trying to understand how something works. I love doing that in high school, especially with rocketry. I loved digging down into the details and all these little things that I eventually kind of learned about when I got to college. But as a high schooler, I did it for the sake of, I was curious. I just wanted to know how the darn thing worked. I wanted to know how rockets worked. I wanted to know how propellant worked. I somewhat even convinced one of my high school chemistry teachers to let me build my own rocket motor in the chemistry lab, and I didn't blow anything up. So I mean, this is kind of how it was. I was told after a moment, it's like, you can't have this here. This is a bomb if it doesn't work correctly. So maybe that high school mentality of not having really the full awareness of like how dangerous something would be, because they're like, oh, this is so cool. I just love this. But I mean, it definitely helps, whether it's a scientist or an engineer mentality. We type of personalities, we want to know how something works, and whether that is tearing apart an engine or trying to figure out why this chemical reaction works the way it is. It's just how our minds work. We're just curious about how nature works and how all these things interact. And in my case, it's how do I take all these natural phenomenons related to how electricity, magnetism, and physics works, and how do I turn it into a spacecraft? That's where the education part in college and the experience turns into, I know how to actually do that.
Great. And so is there anything, it sounds like you were spot on with the things that you knew that you needed to do and the goals that you outlined for yourself, but what advice would you have given a young Michael Staab? Would it have been to stop and have fun earlier, or to work harder on certain things, or looking back? What advice? And remember, it's not just for you, but for students like you.
I would have told myself, if I could look back, let's see, when was I in high school? So if I could go back 16 some years, I'm going to age myself a little bit here. If I go back 16 years and I told my high school self, in that sort of very, that very curious mindset of still being, trying to figure out how things work, I would tell him to keep doing exactly what you're doing. Because in the end, it's going to pay off. My career has been everything I had hoped it would be when I was in middle school and high school. It's turned out, I mean, we're in sort of a renaissance space age again with all this commercial stuff going on. It's everything I hope to be. Literally, it's everything I would hope it would turn out to be. I absolutely love what I do every day. There's some road bumps along the way of, is engineering really something I want to do, because it was really hard sometimes. But at the end of the day, you're like, yeah, I love doing this so much. I wouldn't have changed anything with what I was doing.
Awesome. All right. Well, thank you for all of that. And Sandy, do you want to take it from here?
Yeah, I love that. I'm going to age myself and go back 72 years for my high school self. I love it.
Yeah, I have to think about it. It's just like, wow, I can't believe it's been almost 2 decades at this point.
Totally. I mean, and I really appreciate the thought about like, keep doing what you're doing and you will get there. And so like transitioning from young learners to business professionals, and Mimi, please chime in anytime, of course. You've been in a position, Michael, where you've been in a leadership position in a number of different capacities. You've very likely worked with some A+ top tier leaders as well. What are the character traits of a good leader, either on a mission or the business world, or just in life in general, as you see it?
the best leads I've ever had on a team, they set up a great team and then they're hands off. If you set up your team correctly, you never really need to be involved with day-to-day management of what's going on. Because if you've got good people in place, they know what they're doing, they know what they need to do, and everything else can work very smoothly. When I was on Cassini, great project manager, great spacecraft team chief. Things just worked very smoothly because they had good people. Everyone knew what the directives were to get the work done, and we flew a flawless mission to the end. Being a past flight director and being in more developmental roles in sort of a leadership role, best important thing is to listen. Best leaders are not ones that just kind of crack a whip from the throne. It's getting into the trenches. It's listening to your people, understanding what the problems are, and communicating well with others outside of your organization. I mean, engineering is a team effort. You're going to work with hundreds of other people that all focus on their own little discipline, and all they care about is their little discipline. And the important thing from an assistant engineer role and from a team lead role is that put together a good team, listen to your people when there are problems, and make sure that you communicate well to everybody else. And that's what keeps the machine working so flawlessly, or at least that's the idea.
Thank you for that. So speaking of the machine, and then also speaking of the notion of being hands-off, listening, and then simultaneously setting other people up to succeed. In a lot of businesses now, in like the working world, people are being told to do more with less, and they're working on projects, in some cases, like, all day and all night. When you're working on an ongoing project that potentially has a 24/7 capacity, and you're working with different teams who might be rotating, or you're working with different folks, how do you work through problems as they happen and then simultaneously set the next team up to succeed, to kind of carry the baton? So it's like you're running this relay race where you're solving problems, but then you have to pass the baton very gracefully to the next leader to take care over and carry that work forward. What's your mindset, and how do you sort of approach that?
Yeah, so in just speaking from flight director days, one of the most important qualities I looked for in another flight director was this sort of calm mindset. Day-to-day operations, most of the time, nothing bad's going to happen. But when that one terrible thing does happen, you learn a lot about not only yourself, but you learn a lot about your team. Is there panic? Is there a lot of indecision making? Is there just a lot of just don't know what they're doing? Good flight teams, we are trained to know what to do in an emergency. Pretty much any credible emergency we know can happen. We have either assessed it and we know what the plan is, or we have reviewed it in a test environment. We know what to do. So when typically, if there's we can have little things happen on a vehicle. Oh, this thing turned off, or it cycled, or it just had this little reset. Not a big deal. We take good notes. We pass that information off to the next flight director, and just say, like, hey, these are things that happened. These are the activities that are coming up the next day. This is the data you should expect to see. These are the activities you should see within the data. This is when the vehicle should communicate. If those things don't happen, we of course have contingencies. If it's an ongoing problem, like when we have the storm on Mars, I was in a sort of the lead flight director, so I had sort of the overall understanding of what was going on with the vehicle, and I knew what the plans were from a day-to-day, a week-to-week, or some points, a month-to-month basis, kind of what we were playing on the horizon. The important thing is just to keep the rest of the team, as I did, just kept the flight directors, this is what we're doing. These are the plans that are coming up ahead. When we're planning what we're going to do for the day, we're going to stick with the plans. These are, if something happens, this is what we should expect to see. And then from a long-term planning perspective, we looked at, okay, if we don't hear anything by this month, we're gonna start doing this thing. If we don't hear anything by this month, we're gonna do this thing, and we're testing and doing things on the side, aside from the team that's physically working problem in time. So it's just about what I look for a good leader is someone that is calm and cool, because when it hits the fan, sometimes it hits the fan hard. You're going to learn a lot about your team and how well technically they're situated and how well they work under pressure. That's a trait for not only a good flight director, that's a trait for anyone who operates in highly risky operational environments, whether it's flying airplanes or as an astronaut, those high risk environments. If you got someone that panics at the first sign of trouble, you're probably in big trouble.
Yeah, thank you for that. The calm is really interesting. I mean, not to go too deep into the metaphor, but the calm before the storm. And you mentioned the storm that, hit Opportunity when you were in mission control. And last time we spoke, you kind of teed up the notion that event really showcased teamwork, crisis management, the ability to problem solve really quickly. Could you talk a little bit about sort of what happened, how you and the team responded to it, and what your advice would be sort of based on that?
Yeah, so we had just passed our 14th year on the surface. We had just gotten through 5,000 days of operations on the surface. Everything was going. Didn't foresee, we were finishing up a big science campaign. Everything was going great. And then one day we came in, we looked at the data, and our power numbers had dropped significantly. And we got some images from the orbiters at Mars, and we saw this massive dust column moving down from the North Pole towards the site where the rover was. And we're solar powered. You need the sun to generate our power. As we went through the week, we saw our power numbers continue to dip dramatically. I think in the span of a week, we had lost over 400 watt hours of power from the first day we saw the storm until the last day we were in contact with it. And at that time, we're generating only maybe 450 watt hours of power at best. So we're watching as the rover is very slowly dying, and there's nothing we can do about it. So I was the flight director that week. Just so happened that I was the flight director that week. That's just how the rotation shifts. We took different approaches throughout the week as we saw the power dipping. One of them was, keep trying to talk with the vehicle every day, get rid of anything that's not necessary in terms of keeping the vehicle up. We call shedding all non-critical activities. Take some images of the sun so we know how much dust is in the air. Get a couple of the data products we need to figure out how well the solar arrays are working, how much energy we're generating, and shut down. So the process for the first couple of days was minimize power. And then when we realized that even that wasn't going to help us, we were going to lose contact with the vehicle no matter what we did. The priority shifted to get as much data off the vehicle as we could, so that we had a plan to start with when we lost contact of when we were going to hear from the vehicle again, what we were going to do, all those other things. There was a time when there's a lot of too many cooks in the kitchen, too many people in the room when everything was happening. Sometimes you have to make the tough calls as a flight director, where you basically even tell the project manager to leave the room because it's becoming a distraction. It's not helping anybody, and everyone trying to voice what we should do is not helpful. We have plans, we have procedures in place. We know what to do when these types of situations happen. So we cleared out the room. Team put our heads down. We got to work. If we need extra help, we called it in. But other than that, it's just a great example of team working very well. following the training that we had, getting assistance where we needed it. And after we lost contact with the vehicle, we followed this very methodical step-by-step plan, reviewing it with NASA about what we were going to do when we heard from the vehicle again, how we were going to hear from it, what those signals were going to look like. And from there, we built our plans up, and we had all these different types of procedures on the shelf. And when we heard things, these are things we're going to do. And just a very methodical, we hear from the vehicle, we get the vehicle back under control, and then we slowly try to recover it and commission it again so that we can back off. Obviously, we didn't get to that port, as we never heard from the vehicle again after June 10th. I think June 10th was the last time we heard from it. We got the first indication that the storm was over us, I think, on June 3rd and 4th, and June 10th was the very last time we heard from it. Not necessarily to say that we did anything wrong. Solar powered vehicle. I mean, if there's a dust cloud as thick as flour sitting over the top of you, and it's just settling on your panels, there's not much you can do. But we followed the procedures. We had a very good plan to recover it. I think the important lesson there is that, even if you do everything right, sometimes you're not going to succeed. That's just the way, that's just life. You can have all the best plans laid out. You can have the best team, you can have the best procedures laid out. And sometimes it's not going to work. You're not going to win. And that's not an indication of failure, not an indication that you did anything wrong. That's just life. It's just how things work out sometimes.
It's a really good distinction between success and failure, and then an event that happens that isn't necessarily a failure. It's just that it didn't succeed in the way you thought. And that's a really, really useful distinction, I think, for folks as they look to kind of quote unquote like work as a team to avoid failure and things like that. But sometimes events happen that you just can't foresee. Yeah, go ahead.
Yeah, I mean, spaceflight is, we talk about spaceflight as risk management. We can't completely eliminate risk. We can't completely eliminate the potential that we could lose the spacecraft, we could lose the crew. As we go further out into the solar system, that is going to become more of a reality. I think that's where NASA's kind of starting to try to redefine what they consider, what is an acceptable loss of crew. Because if we go back to the moon, as we go back to Mars, that those numbers are likely going to have to increase, because we can't possibly build a system that is 100% foolproof that a crew is not going to die. It's just the nature of the work. And the military operates in the same manner. It's all about operational risk acceptance. So we tolerate risk, and we plan how we design things that is what we consider an acceptable level of risk. We can't eliminate all of it, but we can certainly control the things that we can't control and try to reduce the risk of losing the spacecraft, the vehicle, or the spacecraft.
It's fascinating to hear that distinction. Just a quick build on that, and this isn't necessarily on the Q&A sheet, but this reminds me of a conversation maybe that we had with Jerry Bostic, who's a flight controller, and he talked about the distinction between being reckless and taking a risk that you can manage. So it's like risky versus recklessness. And I was wondering what your thoughts on that distinction, because you're talking about being in the epicenter of programming and engineering that's going to take people farther than we've ever been. How do you manage that distinction between taking a managed risk and then also making sure that things aren't reckless, going too quickly?
So the only way we can completely eliminate all risk in spaceflight is we never fly. But that's no fun. And that certainly doesn't accomplish the things that we want to go out and see. The difference between recklessness and controlled risk. Recklessness is knowing that something has a high risk of failure and just flying it anyway, knowing that there's a high probability that something bad could happen, and it could kill the crew. It could injure or kill spectators on the ground. It could damage tremendous amounts of property. There's a difference between controlling that risk and understanding that, something landing a human on the moon risky. It's dangerous, especially in the South Pole, where there's not great line of sight for contact. The crew is basically on its own to try and manage those things. We can make our systems as fault tolerant as possible. We can reduce the credibility that a part is going to fail or that a system is going to fail as much as we can. And we have means within engineering to bring down the risk, to try and get it from a least acceptable to a more acceptable area. But at the end of the day, we can't get rid of all of it. So based on sound engineering analysis and good engineering judgment, we can say that, the probability of this happening is very low. And we have done everything from an engineering perspective to reduce the risk of that hazard occurring as much as possible. On the other side, the recklessness part is, we know that this thing likely, there's a difference between there's a 1 in 100 chance this could happen and a 1 in 3 chance. We know that there are ways that we can mitigate that risk. We know there are ways that we can reduce the likelihood of that happening, and just saying, let's just go do it yourself. The term that I use when it comes to this is, if I myself would never fly on the vehicle, how could I ask an astronaut with family and children and spouses to get on that vehicle if I myself would not get on myself? If it's a case of I myself would never get on that vehicle, I could never ask an astronaut or a pilot to get on it myself.
Yeah, that's a probably a really solid benchmark, out of the gates for something that, when you're building it, and then also saying, okay, this is sort of passing our criteria. Something that's like able to actually fly and service. And if you're not going to get on it, why would you ask somebody else to?
Yeah. I mean, I've told that to people I work with as well, is, we're building a lunar space station. People are going to live here for up to 30 days. If we would not be comfortable sitting on that vehicle for 30 days, if I thought that if I were to go to Halo and I knew something of a high likelihood that there is a ticking time bomb in here that could kill me, if I wouldn't be willing to go on it, I would never expect an astronaut to go there.
Mm-hmm.
But we're very good at our jobs, and we take these things very seriously. We use very methodical engineering analysis and very methodical engineering judgment to eliminate as many of those risks as possible, and the ones we can eliminate to reduce the likelihood of it
Yeah. Thank you for that. Moving to the prep for Mars missions, there was one question I had about the phases of launch and the building of software in parallel around as you prepare for EDL, the entry, descent, and landing. And then Mimi, I want to hand it to you for other questions on your punch list. But Michael, I'm going to say 6 months ago when we chatted, you were talking about the fact that in some missions, you would send a rocket into space with a rover, and then as it's flying to Mars, you will continually program and send software to the rover to prepare for EDL, which is fascinating. And that draws a lot of parallels between businesses that are releasing products and beta versions and beta testing and that sort of thing. I was curious about how done is done when you're getting ready for launch. What's an acceptable item on the punch list that you're like, we know we can get to that in a week or two, and we have more time in the world. Then you're also talking about the commanding moratorium, which I'm interested in hearing about as well, which is like, no more changes, we're locking it in, and then it's happening one way or the other. So I was wondering if you could talk a bit about that process and your thoughts, and I want to hand it to Mimi for other builds.
So we know that when we launch a vehicle to Mars, for instance, we have 6 to 8 months before it's going to get there. As you're going through your launch campaign to get your vehicle ready to fly, the important things are to finish the integration of the vehicle, getting what we call the cruise software on board, and that's what it needs to fly out to Mars, and to get the vehicle launched, because we have a very short time window. When you use chemical rockets, you have a 3-week period roughly every 26 months to get to Mars. there are other, depending on where you're going, there are other types of launch constraints. But the point is that the most important thing when you're getting into a launch campaign is you got to get the vehicle in the air. You got to get off. When you know that you have another 6 to 8 months before you arrive, we can spread out the priority right now is to get this build of flight software done. We can worry about the other one when we get a little bit further down the line because we have more time to work on it. The priority is get the vehicle launched. And then EDL is many, many, many months down the road. We have time. We have margin in our schedule that we already built as part of the program to build the software needed to get the vehicle to the ground. And we know that because we plan for it and we test for it and we have sufficient time to get it built, get it verified, get it tested, and get it on the vehicle. For the command moratorium, this is sort of something that gets into what I do for a living for management and system design and things like that. When a vehicle is getting ready for a critical event, and that is an event where you have to complete it for the mission to be successful. So if you're trying to land on the surface of Mars, there is a roughly 7-minute time period from when you touch the top of Mars's atmosphere until you are on the surface. And that's not something that you can pause, say like, oh, I had a problem with the vehicle while it was cruising. I have weeks to figure out what the problem is because I'm just cruising, I'm not doing anything. But with landing on the surface, physics, gravity is going to pull you down to the surface. And if you don't figure out what your problem is and get down to the surface, you're going to crash. There is nothing we can do to stop that. Most programs that prepare for a critical event, we institute what's called a command moratorium, which says that within this much time before the vehicle does this critical event, we're not allowed to change the state of the spacecraft. We're not allowed to command any changes on board because if there's a problem, we don't have enough time to simulate the problem on a test bed or a flat sat. It's basically it's a mirror image of the spacecraft, just without maybe all the structure, but it's got all the electronics, it's got all the circuit cards, it's got all the flight software. If there's a problem, we don't have enough time to replicate that problem and figure out what's wrong with it in order to fix it. So we say within this much time, we know what the state of the spacecraft is as it is going into this critical event. And one way or another, it's going to do it, whether it's successful or not.
It's fascinating. There's so many takeaways, I think, for business professionals, Mimi, who are told to launch now and decide, it's okay, we can fix this later. But really, there is a distinction between things that go out really, really quickly. And then there's a time in projects when there can't be any more changes. So
it's what is the priority for the mission right now? The priority is to get the vehicle off ground and get it cruising out to Mars. We can deal with other problems later. Cassini was the same way. The software Cassini needed to insert into Saturn and run its science mission wasn't delivered to the spacecraft until 6.5 years roughly after it launched. So they had 7 years before they got to Mars. They had plenty of time to work out all those little details. They didn't have time to do as they were building the spacecraft. Get the spacecraft built, get it on the launch pad, get it on its way, and then we can deal with those other problems later.
But that is fascinating. And I don't think anybody would conceive of that's 7 years. You're probably not even thinking of who you're going to hire to actually do that. If you think of a 7-year cycle in an organization, you haven't put the job posting out yet for the person that you need to actually complete that task, which is just fascinating. I think for folks who work in regular companies, that's kind of mind-blowing.
Limitations that you'd impose on yourself if you did try to set standards or at least the parameters for that software before launch, you would fail to take into consideration all the advancements in technology in the following years. So I wondered if you use the term in your industry, mostly viable product.
Mm-hmm.
You do.
We think a spacecraft is as very famous Jay Piller would say, his name is Gentry. I think he still pops around. He's like 90 years old. He'll never retire. He said, "What is the least acceptable option?" So what is the essentially, what is the minimum viable solution here that meets all of the requirements from the science community, meets all the requirements from the engineering community to get the vehicle off the ground and on its way. And we can figure out the other problems later. Because for most interplanetary missions, we have lots of time before it gets to its destination. We have time to figure out all these other little problems. We can work those later. Get the minimum viable solution. Get the least unacceptable solution up into orbit on its way, and then we can figure out all those things later.
Right, the least unacceptable. That's great. Well, and I think of not just that the whole purpose, the whole focus then also unites the team, and that the focus is to just launch, just get it on its way, and we'll figure it out. I can think of business initiatives, government initiatives, all kinds of parallels to that. One other thing I wanted to ask, Sandy and I have been hearing a lot from the Mercury, Gemini, and Apollo days about simulations. And you mentioned earlier in our conversation that that there was rarely something that you hadn't reviewed or experienced in a test environment. So tell us about the role of testing and simulations, and even during the Opportunity dust storm, when you were you running simulations then, and how did that impact your work?
Well, testing is the way that engineers prove that the thing that we designed works as we said it will. So we will, without getting into the details of the systems engineering process, we will take a concept and we'll decompose that down into lower level functions. So we create a functional architecture, we define requirements, we create a physical architecture, which is the actual spacecraft itself. And we have, CAD drawings, we have documents that describe behaviors and what flight software we're going to use, and how a part is supposed to work, how much it's supposed to weigh, how much power it's going to take. All these very, very intricate details of engineering details of how the thing works. We use testing, what we call actual verification, to prove that the thing that we designed is exactly what we said it was going to be in our specifications. So we can use different types of techniques, whether it's analysis or simulation or an actual component that we put on a test bed or a flat stat that replicates the behavior exactly of what the part or what the spacecraft's supposed to do. And we can verify, we can prove that the thing that we designed works exactly as we intended to. With Opportunity, we had a vehicle that was on Mars already. It'd been there for 14 years. We had its original test bed, which is now at the Smithsonian. But it's essentially this, it is an exact replica of the rover. So we built 3 rovers when the program was formed. We were going to build 3 rovers. 2 were going to Mars. 1 was going to stay here on Earth. And that's what we use to basically do any tests on the vehicle before we send it up to Mars, because we can test something out as long as we need to on Earth to make sure that it works correctly. We only get one chance when we send it up to Mars, because whatever that thing is we're trying to do, we want to make sure it works correctly first time. With the dust storm, we had an initial state. We knew what the vehicle was in when we last heard from it, and we knew what the spacecraft was going to do, because all the design documentation said this is what the spacecraft will do, and that was all programmed in the vehicle. So we took that information and we basically started probing questions, basically setting up the vehicle in such a way that we said, okay, if it wakes up at this time and it believes it has this fault on board, it's going to do these things. And from there, we can simulate when we believe the vehicle is going to wake up again, how long it's going to wake up, what that signal is going to look like. We can test how would we recover the vehicle once we hear from it. What are the steps we're going to do? We can verify the timing of we can first verify that the command structure that we created is correct. and also verify that the timing is correct so that we make sure that if we expect the vehicle is going to be awake here, we're going to be able to get the commands in at this time, and those commands are going to finish executing before it shuts down again. So that's what we use the test beds for. So we use basically anything before it goes to the spacecraft will be tested on the ground before it goes up there. So we make sure that our command structuring is right, and our sequencing or timing is correct, so we don't do something on the spacecraft that we don't want to do.
That makes great sense. Well, I just have one very lighthearted question for the last of mine, Sandy, and that's so I found out through getting to know Sandy a bit better that I don't think you're a hoarder. You're much too neat a person to have been a hoarder, Sandy Marshall, but he does keep things of great sentimental value. So that includes his binder from camp. He even has his acceptance letter from camp and his jacket from camp. And he has some very specific memories from Cosmosphere camp that he still carries today. So do you have any top memories that you can share of your time at camp? And if you saved anything from your camp years, what was it?
Well, I actually have a framed sort of memorial of all of my graduation certificates, all of my patches, my flight wings. I have everything sort of memorialized there because it was a really special time for me. I knew what I wanted to do in high school, but the camps kind of really solidified. It's like, yeah, I'm exactly where I'm supposed to be. This is exactly what I should be doing.
So was there one moment at Cosmosphere camp that, or at that time, I guess it was FAT-P, that brought that home for you?
There was, so during the old FAT-P level 2 camp, I think between the scuba diving and going on the centrifuge, my inner ear did not like me. And I ended up passing out during, I think one of the Falcon, I think we were doing one of the sims on the ground. And Teresa Sindelar was my camp director. And Space Camp Brett was my camp counselor. He's still there. He's never going away. Everybody's freaking out. And T puts me in the car and takes me over to the Hutchinson Hospital. They check me out. Well, nothing's wrong with me. Of course, this happened on my parents' anniversary. So I ruined another parents' anniversary. I think this was the second one I ruined it in like 5 years. But afterwards, I got to really know T really well. And she is a lifelong friend. I always told her that, you know, I'm still applying for the astronaut program down there, because hopefully, you know, we can take a picture someday that's like, look, here's one of my little space campers who's now actual astronaut that I am training to go to the space station. So I always thought that was cool. It made a lot of really good memories with, you know, people I still keep in touch with. A lot of the counselors that I worked with when I was a counselor there, and several of the directors I still keep in touch with. You know, they keep asking me, you know, you're an astronaut yet? And it's like, well, no, I'm not quite there yet. But you know, if it does happen, you know, we can all get reunions some days. Like, look, here is the Kansas Cosmosphere's very first actual living, breathing astronaut.
Right, our first alum in space. Oh my gosh, that would be so exciting. Please don't forget us when that happens.